Talking about what science is. There will be a brief question about this on your third exam, and this is the topic for your paper. So, believe it or not, you now have a pretty complete vocabulary to talk about the physical sciences. Energy, motion, force, momentum, these are ideas that come back again and again and again. And you will use the language that you've developed so far in this class to discuss all sorts of things in science and engineering throughout your careers. Whether you're talking about chemical engineering, you're still going to be talking about the force applied by the van der Waals force and hydrogen bonds and so on. If you're doing bioengineering, you're going to be interested in the energy required to do different things and so on. But the development of what we have done so far, really paralleled the birth of science. The modern scientific method emerged in a story that kind of ended with the work of Isaac Newton and maybe, people 100 years after that consolidating the ideas. Isaac Newton was kind of a pivotal figure. There was a biographer who said Newton was not the first of the modern scientists, Newton was the last of the old magicians. Because when he wasn't doing laws of mechanics and so on, Newton was like interested in alchemy and how to live forever and how to turn lead into gold kind of topics. He was very much a mystic, in addition to being really, really like to us almost uh, inconceivably good at mathematics without algebra to help him. Martina, I saw that you just sent me an email. I'll look at it after class. I saw the subject was cool video, so I will look at your cool video after class. Um, and this, what you see on your left here is kind of a the difference between science and other ways of doing things. You know, pull a lever, get zapped. Most people would say, I guess I shouldn't do that. And the scientist says, I wonder if it happens every time, and goes to pull the lever again. Um, so I'm going to ask you now. I'd like you to type in chat, and we will go back and take a look at the back scroll, and people will get small amounts of extra credit for good answers here. Uh, what do you think, in your own experience, what science is, how it's different from other ways of examining our world, and what science looks like when it's being done well? So take a minute, ponder this, and type what you have to say in chat. Fence says science is the study of how things work. Benjamin says scientific ideas are replicated. You can do them again, and you have things that are simple to understand and useful. Um, Daniel says the study of the world mechanics uses hard facts instead of theory. Zachary says it explains how our universe works in a way that proves our explanations and doesn't just assume stuff. Megan says that it looks repetitive and specific in that components are being analyzed and givens are being tested. So this emphasis on detail. So scrolling too fast for me to read now. Science breaks down the world around us. It involves physical and visual examination. Christina says science is humans figuring out why the universe works in the way it does. Um, Martina is again getting to this idea of reductionism, of taking apart the universe and looking at its smallest pieces. Um, Vincent emphasizes observations and experiments and studying systematic things. Ryan says that he was a bomb technician. Oh, wow. And it was your job to think about problems and testing your theories to solve them. Your counterparts were more smash and not think about it. Yeah, if you're diffusing bombs, that smash and not think about it is not a good idea when the thing you're working with tends to smash back. Um, Annie is emphasizing understanding why something works, understanding model building, and again this idea of replicating something, looking at results multiple times. Eliot is talking about science rationalizing things and making sense of the world. Yeah, I mean the basic premise of the whole scientific method. It's so obvious we don't even think about it. But the thing that really kicked off the scientific revolution was people saying, let's assume that our world is something we can understand. Because if we think that lightning is Zeus throwing thunderbolts because he's drunk and mad, then we're never going to understand it. But if we start with the assumption that we can understand lightning and then set about to do that, we can actually make progress. So yeah, Eliot's point is really important because science starts with this premise that our world is something we can wrap our brains around. Giachi talks about hypotheses and doing experiments. Shamil emphasizes says theoretical explanation of things. Shelby comes back to repeatability. Jacob says science is the art of discovering the world around us and understanding fundamental properties, cause and effect, repetition. Again, you all are mentioning the ideas that everybody is coming back to are being methodical, repeating results to verify them, and focusing on experiment as a way to give us evidence. Um, uh, Kalhaku talks about science being a way to understand things that are not biased by tradition, where we try not to let our personal backgrounds bias us. Um, yeah, all of these are, again, Jasmine comes back to the thing everyone's talking about: systematic study of the world through experiments and observations. Um, all of you are saying things that are like on my next slides, which is wonderful. Uh, these are key facets to the scientific method, and what I want to do is all of what you are saying here is like true. This is a correct characterization of how science works. What I want to do now is to kind of look at the process of science through a little bit more of a philosophical lens. I want to tell the story of how modern science emerged, and I want to look at the properties of that story. Um, and then at the end, I want to look at a brief example of how science can go wrong. That's what your paper is about. Your paper is about examples of how the scientific process either intentionally or accidentally gets derailed. And we'll talk way more about the paper next week. Um, for those who took Astro 101 with me, it'll be quite similar to the paper you wrote for Astro 101. There'll be a modified assignment for the people who already, did one paper on this in Astro 101. If Kim or Lisa's here, people who I knew took Astro 101 last semester. So I want to take a brief tour through 2,000 years of history, um, in the way that people in the Eastern Mediterranean basin thought about natural philosophy. There are, of course, lots of other approaches to this. I want to contrast the way that ancient Greek astronomy and natural philosophy worked with what emerged in the same place in the world 2,000 years later. So in ancient Greece, um, astronomy, which was kind of the earliest science, was thought of as a different thing from natural philosophy. So astronomy was these mundane questions about how do the stars move in the sky, how do the planets move in the sky, when will there be an eclipse, how can I get sailors home safe at night by looking at the stars, when will Mars rise tomorrow because something something horoscopes. And the Greek philosophers didn't see this as a super lofty thing. You had to get your hands dirty with numbers and data, and in this society, it was thought of as more elegant to just like sit around and think. So the natural philosophers, people like Aristotle, were more concerned with questions like what is truth? What is beauty? How are truth and beauty the same? And these are very pointed questions. And they had the idea that the best way to get to the underlying truth of existence is to sit around and think very hard and to argue with each other. And the idea that you should go out and look at the stars, and maybe by going out and looking at the stars, you will understand the underlying truth of nature, was a little bit distant from the way they thought. And there was a little bit of a crossover, right? The astronomers had to think. The natural philosophers did make some observations, so Aristotle was not as completely clueless about physics as people think, but there was still this divide. Um, what I want to do now is I want to talk about what astronomy was like in that time. So this is around 0 BC, 0 AD. Much of our knowledge from that time comes from the writings of Claudius Ptolemy. I believe his first name is Claudius. Yeah. He's an interesting character. He carries a royal Egyptian name. He did his work in Egypt. At this time, there was one civilization that spanned both the Eastern Mediterranean basin, so Greece, and Northern Africa, especially in Egypt. And the center of learning at the time was in Alexandria, in what is now Egypt. And Ptolemy wanted to calculate how things in the sky would move. So what he did was he looked at the sky, um, modified kind of what the natural philosophers Aristotle and so on had told him about the Earth being at the center of all existence, and said, okay, how do the stars and planets have to move in order to make them go in this way in the sky? And he was able to deduce what their patterns were, but he explained them in a very complicated way. Um, but the explanations that he had, the mathematical explanations that he had, there were charts and tables in this book called the Almagest that you could use to predict how the planets would move in the sky. He made some mistakes because Greek mathematics was pretty good but not great. Those mistakes were fixed up by Muslim astronomers who continued to make observations for centuries afterwards, and refined mathematics and developed like algebra, the basis of our modern way of calculating. That word comes from Arabic. That was an invention by medieval Muslim scholars. So we have this model from Ptolemy. Earth is at the center. All the planets move in very complicated patterns around Earth. And the remarkable thing is that in the 1500s, Ptolemy's model, even though it's completely wrong about what thing is at the center of the solar system, you could still get accurate calculations of where Mars would be in the sky from it. But it was really complicated because the planets moved in these weird loop-the-loop patterns. And 1500 years later, Copernicus said, hey, maybe the sun is at the middle and all the planets go around the sun in circles. Copernicus assumed it was circles because the Greek philosophers had said, well, circles are the most perfect figure. And since the heavens must be perfect, because this is like the work of the divine creation up there, the heavens are perfect, everything up there must go in circles. Obvious assumption, right? This was kind of how people thought at the time. And so you put the sun at the middle, you have all the planets, including Earth, go around the sun in circles. And this got the rough details of the motion of the planets right, but the details were wrong. And the publisher added this really weird preface. Copernicus didn't write this, his publisher did. The publisher wrote, "This is an unusual idea, but it is just mathematics." There is a not that's missing from my slide here. It should not be judged on whether or not it makes accurate predictions. Sorry, the not is not here. I was right in the beginning. I need more sleep. Publisher said, this is unusual, but it's just mathematics. You should judge it on whether it makes accurate predictions, not whether it's actually true. And to our modern ideas, right, that's a really weird claim to say, don't judge me on whether I'm correct or not, judge me on whether I make accurate predictions, right? Because all of you have told me that the scientific method relies on comparing theories to observations and experiments. But then, going forward, a couple of things happened. And I want to focus on the second point. Tycho, Sophie, and Kepler made super precise measurements of the motions of the planets. And Kepler, one of those, had a dilemma. He really believed in Copernicus's model, with the sun at the middle and planets going in circles around it. But he was there and he measured their motions, and he knew how good those data were. And he saw that no arrangement of circular orbits could fit the data. That no matter what he did with circles, as much as he thought that had to be the answer, it didn't match the motion of Mars. Mars's position was always wrong by at least an eighth of a degree. Now, he could have given up. He could have said, well, an eighth of a degree is good enough. But he said, I have to question my beliefs. If they don't match the data, I've got to discard them. And he realized that if, instead of using circles, he used ellipses for the motions of the planets, everything fit. And it turns out ellipses are, in fact, the way the planets moved. So he didn't understand why, but now he had at least a knowledge of the motion of the planets. But Isaac Newton was good enough at mathematics. And after there, we were off to the races, and Newton deduced the laws of motion and the law of gravity from those observations and experiments he had done on Earth. And then we're off to the races with the story that you all know. What I want to do now is I want to take that tale of how we got here, how we figured out that the sun was at the center of the solar system, that the planets move in ellipses around the sun, and that all of that is governed by the law of universal gravitation and F equals ma, and squeeze that story, because that's also the birth of science, and squeeze that story for how the scientific reasoning of Kepler and Newton was different from other sorts of figuring out things about our world, because that will kind of give us an insight into the properties of the scientific method. So there are four broad properties of science that I see in this story and going forward. Other people who do philosophy of science may characterize other properties of science, but these are what I see as the main four. The first one is the one that you all kept coming back to, empiricism. That the ultimate authority in science is what we measure about the world around us, what we see, and what our experiments tell us, not what we think. Remember, the problem that the Greek natural philosophers had is that they were too reluctant to go do experiments. They were more concerned with what they thought than what they actually saw. And Jasmine's last comment in chat is exactly this. The second broad property is the idea that you need to question yourself, that you need to be skeptical of your own ideas. And we see this in Kepler's constant questioning of his belief that the planet's motions were circles. He thought that was true, but he was constantly trying to poke holes in it until he figured out that they were in fact ellipses. The third property is universality. The idea that whatever the laws of nature are, that they apply everywhere. And we see this in Newton's laws of motion. Newton's big leap, right? The thing that Newton is famous for more than anything else is the thing with the apple, right? The realization that an apple falls off of a tree for the same reason that the moon goes around the Earth. that all gravitation is kind of the same, whether it is on Earth or whether it's in the heavens. And now we can extend that to things that are billions of light years away. Gravity works the same way out there too. So the third property is that scientific claims are universal. The fourth is that science tries to be objective. Doesn't always do this perfectly, but it tries. That scientific ideas, or how we judge scientific ideas or scientists, ought not to depend on where we particularly come from. Right? That the way that the sorts of conclusions that a person like myself in Syracuse draws from an experiment, we ought to be able to agree with what somebody in Southeast Asia does 50 years from now. Someone very unlike me, perhaps. So it shouldn't depend on a particular human perspective. Um, is everybody with me so far, or do I need to clarify any of these ideas? Because these properties, we're going to look at these and kind of extract from them some guidelines for how science should be done. These safeguards aren't always followed, right? Sometimes honest scientists slip up. Good, honest people make mistakes. And when they make these mistakes, often they get fooled. But there are also people who are intentionally trying to fool other folks by intentionally warping the process of science to basically generate bullshit to convince other people of things that are not true. And keep both of those in mind as we go forward. One of those principles is that a model is only valid within the realm of data against which it's been checked. So for instance, Newton studied only the solar system. Only this example of gravitation where the motion of the planets is dominated by one super heavy star in the middle. Turns out if you want to understand gravity in other regimes, you've got to check it in other regimes. And that's hard because, yes, the principles of science are universal. If it works this way here, it's going to work this way somewhere else. But you've got to be careful. You need to check gravity with very big things, very small things, very fast things, very slow things. And it turns out sometimes the law of gravity gets modified a little bit. A consequence of self-skepticism is that if you have a claim of something, it's your duty to search for experiments that can maybe prove yourself wrong. Einstein did this with his postulate of general relativity. Einstein said, here is a detailed experiment you can do next time there is a solar eclipse. You'll see some stars in the wrong places. If you don't, then my entire 100-page paper is nonsense. But if you do, this is some evidence that I'm right. So Einstein searched for an experiment that could be done to maybe prove himself wrong. The third principle is one that you all told me about. The idea that since my lab and your lab ought to work the same way, if I do something, it's important for many other scientists to repeat it to make sure I have not made a mistake. This is called reproducibility. The fourth principle, coming from objectivity, is that diversity in the scientific community is important because we all have our biases, we all have our particular perspectives, but the scientific results we get shouldn't depend on our particular perspectives. So if we have a diverse community of scientists working on some problem, then any blind spot that any one of us tends to have because of our background is going to be caught by somebody else. So diversity helps not make mistakes. I want to give you one example of how this can go wrong. We'll talk more about this next week. This is the example that will be on your exam. And this is measurement bias. I'm going to skip this example for the interests of time and instead show you a cartoon. Actually, I will talk about this example. We've got enough time. Um, in the 1980s, people thought that Newton's law of gravity might be modified a little bit based on the type of matter. They proposed something called the fifth force, which was a change to Newton's law of gravity. So we would have, Fg now equals gmm over r squared plus a small correction. But they needed super precise measurements of Earth's gravity near a tower to confirm this. So what did they do? Well, they got a bunch of people with sensitive machines that measured little g to make these measurements of Earth's gravity near this tower. The problem was it had just rained, and there were puddles everywhere. So they didn't put these expensive machines in the puddles, right? Who would want to, break this thousands of dollars piece of equipment? So they sampled in a way that was biased toward higher ground. And that bias meant that these measurements of G were biased, which meant that they got an incorrect conclusion about the fifth force. Once they realized this, once they fixed it, this idea that you had to correct Newton's law of gravity went away. So bias in what measurements you make can convince you of things that are not true. In this case, nobody meant to fool anybody else. They just made a mistake. Once they corrected their mistake, everything was fine. Here's another example from Randall Munroe, another XKCD cartoon, of how this can happen in a funny way. Here, a couple of scientists have a hypothesis that maybe jelly beans cause acne. So she sends the scientists off to investigate, disrupts their Minecraft game. This statement here, that there's no link between jelly beans and acne, p greater than 0.05, this means, well, I've got it down at the bottom, I don't need to write it. This means there's more than a 5% chance that whatever we saw is just a coincidence. So the scientists do this measurement, and it's like, yep, it's settled. We got some difference between the amount of acne that people who do and don't eat jelly beans have, but there's more than a 5% chance it was just an accident. But then this guy says, maybe it's just a color, and sends the scientists back to go do the study. So the scientists, they're scientists because he's got safety goggles on and she's got a clipboard. They study all the colors. No link between purple jelly beans and acne. No link between brown jelly beans and acne. Pink jelly beans and acne. Blue jelly beans and acne. Teal, salmon, red, turquoise, magenta, yellow. Gray, tan, cyan. Whoops. Wait a minute. If you do this with green jelly beans, you find that there's less than a 1 in 20 chance that this was a fluke. You try to see if eating green jelly beans gives you acne. You see a result that says that, there's less than a 5% chance this was a fluke. You've done this with 20 colors in total. So what happens? You looked at 20 different colors of jelly beans. 19 of them you find, there's no link. One of them you find there's a correlation between eating jelly beans and having acne, and this is less than a 5% chance that this was a fluke. Well, of course, if you roll a 20-sided die 20 times, you shouldn't be surprised if you roll a 20 once. But what happens? This is the one everybody gets excited about. This is the one that winds up on the headlines of the newspapers and that people think about. Only a 5% chance of coincidence. Never mind that the other 19 experiments got done. So this bias is particularly common and problematic in medical research. It's gotten better because doctors are very aware of it now. But the core idea is that if you make a biased set of measurements, then your answer is going to be biased too, and you might convince yourself or other people of a conclusion that is flawed. So on exam three, we're going to give you a story. And we're going to tell you a story that involves a biased measurement, and we're going to ask you to identify how that measurement is biased and tell us what effect that bias will have. So that's how this will show up on exam three. What we've done so far is kind of a cursory look at the process of science. We will do this in a lot more depth next week and talk about what your paper will be. So we've got 22 minutes left. I'm going to first ask, um, does anybody have any questions or comments on our whirlwind tour through what science is and how it works? Okay, I'm going to put a cut here in the recording.